Cholesky decomposition. If A is a symmetric positive definite matrix such that, of course, XTAX is greater than or equal to 0, as you saw in the previous video, then A can be decomposed into a symmetric decomposition like this, which is L times L transpose. So basically, you take the lower triangular matrix and multiply it by the transpose of it. And of course, the transpose of a lower triangular is an upper triangular. How this works is by example. I'll show you by example. Let's look at a particular A. So the way this works is we will say that A, of course, is equal to some lower triangular matrix, which we will call define as follows. This would be our lower triangular matrix with these entries L that we need to find. And of course, its transpose would be the matrix multiplying it. So that would make the decomposition. So that would mean we would have something like this. So remember, it's the transpose. So the just to remind you, the column here will become the row here. So this column will become the next row. So this will be and the final, of course, will be. So there now we have this would be our factorization. But the way we find the Cholesky decomposition is by now multiplying these two matrices. And we know that two matrices, like in Doolittle's method, two matrices are equal if each entry, corresponding entry, is equal to each of the entries on the other side. So that means we will have the following situation, where when I first look at the first element, this will be just L11 squared. So we'll have L11 squared, and L11 squared should be equal to 2. This implies that L11 is, of course, square root 2, and of course plus or minus. So we're going to take the positive one for now. We only need one factorization. So we'll take it to be plus. The next element here would be L11, L21. Okay, so L11, L21, sorry. So let me write that down here, L11, L21. And that should be equal to the second element, which is -2. Okay, and we already have L11. This implies that L21, okay, is equal to -√2. Because when you divide across, it'll just work out quite simply. So next, if we move on, the next element is L11, L31. Okay, and that is supposed to be equal to -3. So therefore, this implies that L31 is, of course, -3 over square root 2. So -3 divided by square root 2. Similarly, we'll now come to the second row. The second row will be, of course, starting with L21, L11. Now one thing I'll tell you, this, no need to write this down, because what will happen is L21, L11 is the same as L11, L21, which we already have here, as you'll see. The next one will be L21 squared plus L22 squared. That's a new one, so we'll write that down here. So it's going to be L21 squared plus L22 squared. Okay, and that's equal to 5, of course. So that's equal to 5. Okay, now we already have L21. As you saw here earlier, it's negative square root 2, so that becomes 2. This implies that L22 is in fact square root of 3. It's equal to square root of 3. So that's that found. Next, we'll move to the next one, which is going to give us L21, L31. So L21, L31 plus L22, L32. That's a new one, so we'll write that down. So it's L21, L31 plus L22, L3, 2. And that should be equal to 4, of course. That implies, of course, we already have L21. As you will see, L21 is here, L21, and we have L31. Okay, we have L22, so that we can easily find L32. So this implies that L32 then is equal to 1 over square root 3. So next we'll move on to the final row, and the first element is something we already have used up, L31, L11. So we move on to the next one, which is L31, L21, which we also have in fact used up. So that leaves us with just the one equation, the final one, which is L, all the squares, so L31 squared plus L32 squared plus L33 squared. And that is supposed to be equal to 5. Now, of course, we already have L31, we have L32, so this is quite simple. Then L33 turns out to be equal to 1 over square root 6. Therefore, we get this L. Now, as shown you in earlier videos on the decomposition method, how we do this is as follows. Remember, excuse me. So AX equals B, LLTX equals B, which imply, and we'll put in Y equals, let Y equal LTX, which means that Ly equals B. So we'll solve Ly equals B first. So that would mean that we would have this situation, Ly equals B. So we'll just do forward substitution in this case. So what we're saying is basically, if I put Y here, then this would become Y1, Y2, Y3, and that's supposed to be equal to the right hand side, which is 7 minus 12 minus 12. So now I'll start with the top one first. Square root 2y1 equals 7. So that makes it pretty straightforward, that y1 is equal to 7 over square root 2. And similarly continue, y2, we'll go to the second equation, and when we solve that, we're going to get minus 5 over root 3. And y3, as we go to the third equation, is going to be 1 over square root 6. So we've got our y. Once we have the y, we will go back and solve the next system. So this is the final system to solve. And when we solve it, of course, with back substitution, starting here, starting here, 1 over root 6 x3 equals 1 over root 6, which means x3 equals 1, of course. So clearly we see that it's easy, x3 equals 1. Then we go to the equation above, and that tells us, well, we've got root 3x2 plus 1 over root 3 x3, and that boils down to x2 equals minus 2. And the third, the top equation, gives us equal to, in fact, 3, which means our solution vector is, in fact, 3 minus 2, 1. So here we have a very straightforward example of the Cholesky decomposition, where we end up solving the system, of course, using that decomposition. Now, one caution. Remember that here, Cholesky decomposition depends on the prerequisite. The matrix A must be positive definite. If A is not positive definite, or so if this is dependent on the fact that F it's positive semi-definite. So if it's positive semi-definite, then we expect there to be an answer in this particular case. If it's not positive semi-definite, then L will be complex. There will be elements in L that will be complex. Thank you.